They're not up there? Uh-oh. We've got them. We were hoping you'd have them so you would know which questions you missed. Somebody check one more time, real quick. Humor me. You're on it right now? Not there?
Now, where is
Yeah, what is this thing?
If you run there, try to get there. Okay, we'll try to get them for you. We're going to continue on because we have a limited amount of time this morning. So if you think it's a question you might have missed and you remember what you picked, just remember that. Oh, for my questions, I'm going to ask you guys not to type out the questions and the answers. I'm going to ask you not to take notes specifically on the question. You can take notes on the concepts, but I am trying to create a question bank and I don't want to see my questions appearing on some kind of student-generated exam bank. So I'll go on the honor system. Okay, so to give you an idea of where things shook out, the average score for the exam was 72, which worked out to about 28.6 questions right out of 40. So not as great as we were hoping for, not as bad as it could have been. So you can figure out where you lie kind of within the course distribution. This is the total student performance histogram. Again, we did get a nice bell-shaped curve going here, and you can kind of figure out where your score was relative to your classmates. Anybody have any questions about that? Okay, so we will move on to my questions, starting logically with question number 1. You can take notes. I'm just asking you not to copy down the question and the answers. I'm going to trust that you won't do that. Is that? Take notes on the concepts. Just don't copy down the questions. All right. So question number 1. Following contraction of a typical muscle cell, secondary active transport of calcium out of the cell by the sodium-calcium exchanger is driven by which of the following? Your choices were A, a favorable gradient established by sodium entry through voltage-gated channels, B, a favorable gradient established by sodium hydrogen exchangers, C, a favorable gradient established by sodium potassium HPase pumps, D, a favorable gradient established by plasma membrane calcium HPase pumps, or E, a favorable gradient established by sarcoplasmic reticulum calcium HPase pumps, or circuit pumps. The correct answer here was the sodium potassium pumps, which, as is indicated in this slide, virtually every cell in the body uses the gradient established by the sodium potassium HPase pumps to drive the secondary active transport of other ions and molecules. The next most popular answer was a favorable gradient established by sodium hydrogen exchangers. What's wrong with that? What kind of molecule is a sodium hydrogen exchanger? Is it a primary active transporter? Secondary. You can't use a secondary to drive another secondary. And even if you could, the gradient is going in the wrong way. Okay, so you're pumping sodium inside the cell with the sodium hydrogen exchanger. If you're pumping sodium inside the cell, that's not going to favor pumping more sodium inside the cell via the sodium calcium exchanger. Right. The other answers, favorable gradient established by sodium entry through voltage-gated channels. Nope. Favorable gradient established by plasma membrane calcium HPase pumps. This is a primary active transporter, but you're pumping calcium out. And you also want to move calcium out with the sodium calcium exchanger. This doesn't give you a favorable gradient for doing that. You're already moving calcium to the cytosol, so you're still moving this against a gradient. The circuit pumps, same thing. They're pumping calcium into the intracellular stores, which effectively makes the gradient harder to get calcium out of the cells. That's why these are active processes. Anybody have a question about that one or a comment? Okay. Question number 2. Substance X is an ion found at higher concentrations in the intracellular fluid than the extracellular fluid in the human body. The most likely identity of substance X is inside greater than outside, and potassium is a choice. You should go with potassium. These are the ones that I want you to, it may seem like I'm trying to ask you to remember all of these ions on this chart. The 2 that I really want you to remember right now are the sodium and potassium. And as long as you remember the potassium is very low in and very high out, that should have been where your brain kind of went on this question. And it went pretty well for the most part. I think some people are reversing sodium and potassium potentially. Yeah.
Did you say that potassium is low inside and high outside just now?
Oops. Yeah. If I did, I misspoke. Potassium's high inside, low outside. As you can out right there, which makes sense for function, right? All of these processes that we're talking about, there's high sodium outside the cell that's coming in, high potassium inside the cell that's going out. That's all you have to remember. You don't have to remember the chart. Just remember the physiological processes that are involved, and these questions become more logical. Okay. Question number 3, which of the following is an accurate characteristic of facilitated diffusion? A favorable concentration gradient must be established by sodium potassium HPase pumps for facilitated diffusion of a solute to occur. What kind of process is this describing? It's not facilitated diffusion. This is what happens in secondary active transport, right? You're using the gradient created by primary active transport process to drive movement of another molecule. You already have a favorable gradient for facilitated diffusion. Okay, all the molecules that are moving by facilitated diffusion already have their favorable concentration gradient set up. It's just that they need a carrier protein to get across. B, carrier proteins for facilitated diffusion hydrolyze ATP to move the solute across the lipid bilayer. What's this describing? Primary active transport, right? We don't need to hydrolyze ATP in this case. We don't need an energy source. All we need is a carrier protein. Changes in membrane potential cause the conformational changes in carrier proteins that mediate facilitated diffusion. Nope, don't need a change in voltage. You just need binding of the solute carrier protein to drive the conformational changes. Voltage-gated ion channels, yes, that would be an accurate description. D, facilitated diffusion involves insertion of non-gated pores. Nope, this is just diffusion, simple diffusion through a non-gated pore, something like an aquaporin. So that brings us to E, which was the correct answer. The rate of facilitated diffusion reaches Vmax when all pure proteins are occupied by solute. So here is a basic description of the conformational changes that occur with binding of the solute. And here is our example that once we reach Vmax, 100% of the carrier molecules for facilitated diffusion are bound. Everybody cool on that one? Question number 4. The sodium potassium HPase pump does what? A, establishes a favorable concentration gradient for potassium to enter the cells from the extracellular fluid. Why does that not make sense? Where's the sodium potassium pump pumping potassium into the cell, right? If we're pumping potassium into the cell, is that a favorable gradient for potassium to enter the cell? No, to exit. We'll come back to B. C, maintains molecular neutrality. Nobody went for that one, so that's good. D, provides energy for active transport by hydrolyzing guanosine triphosphate. What's the stem say? It's called the sodium potassium ATPase. So what do you think it cleaves? ATP, adenosine triphosphate. It would be called the sodium potassium GTPase if it was cleaved G. Pumps 2 sodium ions into the cell and 3 potassium ions out of the cell. Nope. Remember, we're pumping, so there's 2 things wrong with this statement. One, we're pumping sodium out, and we're pumping 3 of them out. We're pumping potassium in, and we're pumping 2 of them in. So that brings us to B, helps maintain cell volume by pumping more ions out of the cell than inside the cell. This is correct. So here are the basic characteristics of the pump. Again, highlighting the concentrations, normal concentrations of sodium and potassium in the extracellular and intracellular fluid. And then here we have the characteristics of the sodium potassium ATPase, one of which is to help maintain cell volume. Any questions about that one? Nope. Question number 5. Acetylcholine is released from a presynaptic nerve terminal at a neuromuscular junction, crosses the synaptic cleft, and binds to its receptors on the skeletal muscle fiber. This best exemplifies which of the following types of cell signals: autocrine, endocrine, nanocrine, oligocrine, or paracrine. Thankfully, nobody went for my made-up words, so good. High five on that one. Nobody picked nanocrine or oligocrine. Quite a few of you went for endocrine. This is a signal where the hormone is released and travels through the bloodstream, often some distance to its target. Okay. Autocrine, the signal is released from a cell and acts on that same cell. Auto meaning self, so just keep that in mind. Paracrine, para from the ancient Greek meaning next to, one cell sends out a signal that acts on the cell right next door. And this is classic nervous transmission. Right, you have a presynaptic cell that releases a neurotransmitter that acts on the postsynaptic cell that's right there. So that's what we were describing in this case, was a paracrine. There's a reminder of what these things look like. Anybody have any questions on that one? Question number 6. A 7-year-old boy is brought to the emergency department after 4 hours of wheezing and progressive shortness of breath. He has a history of persistent asthma and is using all of his accessory muscles of respiration upon arrival. An arterial blood gas shows low oxygen saturation and high blood CO2, which if followed would be expected to relax his bronchial smooth muscle and improve his symptoms. So this is an attempt to put a physiological principle in a clinical context. You didn't probably need any of the vignette to actually answer the question. You just needed to think of a signal that relaxes smooth muscle. That was the goal here. So A, inhibition of beta-2 adrenergic receptors in bronchial smooth muscle. What happens when we activate beta-2 adrenergic receptors? Beta-2? Relaxation, right? Beta-2s lead to activation of PKA. Activation of PKA